All right, friends, so taking a look here at our notes for today. The goal of these notes are going to be to calculate the probability of compound events. Now, what are compound events? Well, compound events is just when multiple things are happening. So when two or more events occur, we're trying to find the probability of that. So we need to differentiate between when we have independent events or dependent events. Now, again, what does independent mean? Well, independent means that if one occurs, the probability that the other occurs would not change. So if we remember, the way we prove that is the probability of A given B equals the probability of A. So B has occurred, the probability of A does not change. Right? Now, how do we actually calculate the answer to this if we have compound events? Well, in this case, all we have to do is just multiply the two. So if I want to find the probability of A and B occurring, it would be the probability of A times the probability of B. So let's take a look at an example together. So Mr. Whitesell has a bag of candy that he's willing to share. The bag consists of 2 Tootsie Rolls, 1 Almond Joy, and 1 bag of Skittles. It's your lucky day. Mr. Whitesell allows you to pick some candy. What's the probability that you choose a Tootsie Roll, but you put it back because you don't like Tootsie Rolls, and then you choose a Skittles? Right? Why is this independent? Well, it's independent because we are replacing the Tootsie Roll, right? So the fact that I've chosen a Tootsie Roll does not affect the probability that I will then choose a Skittles because I put that Tootsie Roll back. So let's start and figure out what's the probability of a Tootsie Roll. Okay. So the probability that we get a Tootsie Roll, well, how many Tootsie Rolls do we have? So this is going to be the number of successes over the total number of things. So there are 2 Tootsie Rolls over the total amount of things in the bag is 4. And if you write it as 1/2, that's fine. And then the probability that I choose a Skittles given I chose a Tootsie Roll, well, since I'm replacing this Tootsie Roll, that's going to be the same thing as the probability of a Skittles. So there's 1 Skittles. And again, I put the Tootsie Roll back, so there's still 4 pieces of candy within there. To find the final probability, we would do 2/4 times 1/4, and that would give us 2/16, or you could write it as 1/8, or you could write it as 0.125. Your choice. Your choice. Okay. Any of these, I would accept any of these 3 as the answer. That, obviously not. Okay. Let's take a look at another example. According to the U.S. Department of Transportation, the top 10 airlines in the United States arrive on time 80% of the time. During a vacation, the Gunther family has direct flights to Pittsburgh, Minneapolis, Denver, and Nashville on different days. What is the probability that all of their flights arrive on time? Well, in this case, since they're arriving on different days, we're going to say that these events are independent. Okay, so no big weather storms. The way that I would think through this is just take it one step at a time. So what's the probability that it arrives in Pittsburgh on time? Well, according to the U.S. Department of Transportation statistics, there's an 80% chance of that happening. We're going to multiply that by the probability for the next scenario. So Minneapolis. Different days, we're saying it's independent, so also 80%. For Denver, well, it's also 80%. For Nashville, well, it's also 80%. What's another way we could write this? Since it's independent, they have the same probabilities. We could write it as 0.8 to the 4th, which is equal to 0.4096. Now I know I didn't write probability statements for this. That's okay. All right, you don't have to write a probability statement for this every time. Take a moment, see if you can figure out that last one on your own. All right, so it says during World War II, The British found that the probability that a bomber is lost through enemy action on a mission is 0.05. Okay, only 5% chance of that happening. Assuming that missions are independent, find the probability that a bomber returns safely after 3 missions, but on the 4th does not return. Well, again, the way that I always do this is I just take it one scenario at a time, one mission at a time. So for the first mission, I'm returning safely. Well, what's the probability of that? Well, if this is the probability, sorry, I spoke a little bit quick there. What's the probability that we return safely? If this is the probability that I don't return, then the probability that I return safely would be 95% chance. Right? So that's the first mission. For the second mission, I'm returning safely. For the third mission, I'm returning safely. But for the fourth mission, I'm not returning. So just take it one scenario at a time. And when we multiply all of this out, again, this is the same thing as 0.95 to the third times 0.05. And we find that to be about 4.28%. You can write it as a percent if you want as well. All right, now let's take a look at some dependent scenarios. So for dependent scenarios, the way that we would calculate this is the probability of both events occurring is the product of the first probability times the probability that the second scenario happens after the first has occurred. So really, it would be the probability of A, if A occurs first, times the probability that B then occurs now that we know that A has occurred. Right. If you're finding that confusing, hopefully this scenario should help you out a little bit. So similar scenario. Mr. Whitesell has a bag of candy he's willing to share. The bag consists of 2 Tootsie Rolls, 1 Almond Joy, and 1 Skittles. It's your lucky day, and Mr. Whitesell allows you to pick some candy. What is the probability that you choose a Tootsie Roll and eat it, and then you choose a Skittle? So in this case, we're not replacing that Tootsie Roll, right? We're eating it. So let's think through the scenario one step at a time. So first thing that's happening is I'm choosing a Tootsie Roll. What's the probability of that occurring? Well, once again, there are 2 Tootsie Rolls out of 4 total possibilities. Yay. Scenario 1 done. Now we're going to multiply that by what happens next. Well, now I'm going to choose a Skittles. How many Skittles are there? Well, there's still 1 bag of Skittles left out of. Well, how many total pieces of candy are left? I've eaten one of the Tootsie Rolls, so there's 1 Tootsie Roll, 1 Almond Joy, and then that Skittles that I chose. So 1 out of 3 total chances. Okay. When we multiply that, we get 2 out of 12, which is about, you could leave it as 2 out of 12 or 1 out of 6, but oftentimes we'll write it as a decimal. Okay. 1.67. Alright, now let's take a look at what happens here. So Paul has 3 rock, 4 country, and 2 punk CDs in his car. One day before he starts driving, he pulls 2 CDs from the center console without looking. So we're taking 2 CDs out. What's the probability that both CDs are country? Well, let's think about what could happen in this scenario. So the first CD could be country, which is a 4 in 9 chance of that occurring. Times, all right, I've taken a country, so even though he's pulling them at the same time, I'm treating it as if we're doing one and then the other. So then, what's the probability that the second one is also country? Well, now there are only 3 country CDs left, right, because I've taken one out. And there are only 8 CDs left because I've taken one out. So we get 12 out of 72. And again, you are welcome to reduce that if you'd like to 1/6. But you find that the probability is also, in fact, 1.67. I promise not all of the dependent event answers are 0.167. Oops, sorry, playing around with my Zoom a little bit. Take a look at the last scenario. Pause it for a second. Take a look at that last scenario, see if you can figure it out on your own. Okay, let's take a look. So Mr. Whitesell has 2 donuts to give away. I don't know why that's 2 words. Using a class roster, there are 14 boys and 15 girls in the class. He selects one name, sets it aside, and chooses another name. What is the probability that a girl and then a boy is selected to receive the donut? So this is important. We're saying it's a girl first, then a boy. Right. So let's take a look. We have 15 girls out of 29 total students in the class. Yay, addition. And we have 14 boys. In the second scenario, we only have 14 boys. Okay. Out of, well, I've taken a girl out of the class. She can't get donuts twice. So there are only 28 students left. We get, when we multiply that together, of course, we all know our mental math. 15 times 14 is 100%, 120. And 29 times 28, quickly in our head, we can calculate that to be 812. Right? Easy peasy. I hope you use the calculator for that. When we write that as a decimal, we get 0.258 as our answer. Okay. So let's explore a little bit further about compound events. What if we have some more fun with some Venn diagrams? It's my favorite. Okay. So we're going to let A and B independent events. So we know that they are independent. Okay. And we know that the probability is 0.12. And probability of A is 0.12. We know that the probability of B is 0.6. We want to know, can we fill out the rest of this Venn diagram? All right, we can. We absolutely can. And I'm going to tell you a little hint here. If A and B are independent events, then the probability of A and B, remember that's always where we start when we're filling out these Venn diagrams, is this middle piece right here. But we don't know the probability of A and B, except we do. When they're independent events, we know that the probability of A and B is equal to the probability of A times the probability of B. I want you to try to prove that to me. And I'm going to give you a hint. The hint is that to prove events are independent, we must show that the probability of A given B is equal to the probability of A. Okay. Using that hint, see if you can prove to me that if events are independent, the probability of A and B is equal to the probability of A times the probability of B. Go for it. Okay, so if you're not there yet, pause it. If you're still thinking through, pause it. If not, here's how we work through it. So using our formula sheet, we know that the probability of A given B is the probability of A and B over the probability of B, and we know that that must be equal to the probability of A if we have independent events. See if you can see the next step to prove this now. Well, yeah, using our algebra, if I want to get this by itself, right, I have this by itself, I multiply both sides by the probability of B. And what do you know? These two, this is in the numerator, these two cross out, and I'm left with the probability of A is equal to the probability of A given B. Yay, algebra proofs. All right. I promise you do not need to know this for the test, or you do not need to be able to prove this for the test, but you should know this for the test. So how can we fill this out? Well, let's find the probability of A, and I know there's a lot of stuff written here, and B in this case is going to be 0.12 times 0.6, which is equal to 0.072. Okay. Remember, now we subtract as we go out. Please don't forget that if you have to make a Venn diagram on a test, which you might, hint, hint, nudge, nudge, perhaps a 3-circle Venn diagram, hint, hint, nudge, nudge. All right, so probability of A is 0.12. We subtract this out from that, and we say that just A, the probability of just A, is 0.048. Total probability of B, so this entire circle right here is going to be 0.6. We subtract 0.072 out of that, so the probability that just B occurs is 0.528. And of course, we're never going to forget the outside of our circle, ever, ever, ever. We add these together, subtract from 1, and we find that the probability that none of these things occur, neither A nor B occur, is 35.2%. All right, second scenario. Let A and B be dependent events. The probability of A is equal to 0.12. The probability of B is 0.6. Can we fill in the rest of the Venn diagram? Well, if our scenario is like this, where we do not have mutually exclusive events, again, mutually exclusive events would mean that A and B have no overlap at all, and they're dependent, then this one cannot be done. Okay. And it can't be done. We would need to know either that they're independent events or that they're mutually exclusive events for us to be able to fill in a Venn diagram with just the probability of A and B. Because we don't know what's going to go into that middle. All right, next, really, really important scenario here. Okay, the probability of at least one. So we'll take a look at some scenarios momentarily, but the thing to remember is the probability of at least one, okay, is equal to 1 minus the probability the event doesn't occur. Let's think about that. Let's think through this scenario right here, okay? So Tim and Jane are planning to use their grand prize winnings to take a 4-day ski trip. They want to make sure that it snows on at least one day on their trip. The ski resort they booked says that there's a 65% chance that there will be snow on each day. What is the probability that it will snow at least one day while on their 4-day trip? Well, let's think about how we could do this as a using sample space. Okay, so 4-day trip. So on the first day, it's either going to snow or not, and there's a 65% chance that that happens, okay, which means that there is a 35% chance that it doesn't. So that's the first day. On the second day, it could either snow or not. It could either snow, I don't know why I put a dot there, or not. Okay. And again, this is 0.65, 0.35, 0.65, 0.35. Third day, could either snow or not, 0.65, 0.35, snow or not, snow or not, snow or not. Right. And then on the fourth day, it could either snow or not, 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 and snow or not. All right, sorry, that got really small. And again, we still have 0.65, 0.35. So where are all the scenarios where it snows at least one time? Well, if it snows every day, that's at least one time. If it snows the first 3 days and not on the fourth day, that's at least one time. If it snows the first 2 days, not on the second day, but then on the fourth day, that's at least one. This scenario also is at least one. That's 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 at least one. I'm going through all of them. That's at least one. That's at least one. That's at least one. Oh, here's the only scenario that it doesn't snow at least once. So I could calculate the probability of each of these things occurring, all of those things occurring, and add them up, or I could do 1 minus the opposite, right? So take my one scenario, right? So the probability that it occurs at least once, so probability that it snows at least one day is 1 minus the probability that it does not snow. Does that make sense, hopefully? This is the only scenario where it's not snowing on at least one day. So if I do 1 minus 0.35 to the, well, it has to not snow on every day. That's the only scenario that we're not snowing at least once. We find that, okay, they're pretty safe. It's going to snow on about 98.5% of the days. Okay. Hopefully that makes sense to you. Let's take a look at scenario 2, and then you can look at scenario 3. Okay. So Ms. Gilroy is giving you a 10-question true-false quiz on calculating compound probabilities. Hey, that's something that we're discussing right now. If you guess on every question, what is the probability that you will get at least one correct? So, what's the, always when I'm asking at least one, think about what's the opposite. So the opposite is, we're going to do 1 minus the opposite, the probability that we get none correct, or no question correct. All right, let's figure that out. So 10 questions, what's the probability that I get the first one wrong? Well, that would be 50%. What's the probability that I get the second one wrong? 50%, right? This is an independent scenario. So for each of them, for each of the 10 questions, there's a 50% chance that I get it wrong. So when I calculate this out, I will get about 0.9999. And that is kind of why, that right there, especially true-false, that right there is why sometimes college professors, I don't know if they actually do this anymore, but sometimes college professors will say, if you get every question wrong, I'll still give you 100%. Because the likelihood that you knew nothing, okay, that if you were just guessing, the probability that you get at least one correct is 99.9%. What about if it was a multiple choice? Well, let's say that we have a 5-question multiple choice quiz on calculating compound probabilities. Hey, compound probabilities. Each question has 4 answer choices. If you guess on every question, what's the probability that you get at least one correct? Well, again, we're going to do 1 minus the probability that you get none correct. And in this case, what's the probability that you get, again, if you're having trouble thinking through it, think about the first scenario. Okay, I need to get all of them wrong. That's the only scenario that is not at least one correct. So the first, what's the probability to get the first one wrong? 4 answer choices, multiple choice, one of them is right. So 3 out of the 4 are 75% chance that I guess and get them wrong. For the second scenario, 75% chance. Third scenario, 75% chance. Fourth scenario, 75% chance that I get it wrong. Fifth scenario, 75% chance. So I can just use my shorthand, yay exponents, right? And we find that when we calculate this out, there is a 76.3% chance that you're going to get at least one of them right. Yay, we got at least one right. If you want, you can calculate what's the probability that you guess all of them right and see how small that is. Study for your quizzes and tests. And we do not have a quiz on compound probabilities. Right? All right, let's take a look at one more example together, and then I'll let you work on the one on the back on your own. So, university professor fails 20% of his students on the final. Yay, college. After the final, he polls the students and asks how many of them studied more than 3 hours for it. Of those who passed the final, 72% said that they studied for it. Of those who failed the final, 31% said that they studied for 3 hours or more. Right? So we got a pretty complicated thing going on here, right? We've got a pretty complicated thing going on here. Okay? Where we have some dependent probabilities here, right? If I passed, then there's a certain probability that I studied more than 3 hours for it. If I failed, then there's a different probability that I studied 3 hours for it. So when you're given these conditions, the least complicated method for calculating the probability is by creating a tree diagram. I love tree diagrams. Okay. That's what I recommend doing when you're given a scenario like this. Okay. What's the first piece of information that we've been given? Well, that our university professor fails it. So let's let F equal fail, P equal pass, and then the next piece of information is studied. So S equals studied greater than 3 hours, and let's say N is, well, you can just say studied less than 3 hours. Okay. Now we'll make our tree diagram. Got my fail, got my pass. Professor's failing 20%, which means he passed 80%. Hey! I shouldn't say he failed and he passed. I should say 20% of the students failed the test, 80% passed. That's on them. All right. Of those who passed the final, so we're looking at passed, 72% said they studied for more than 3 hours for it. So we got our S here, and we know that 72% there. All right. Down here, well, if 72% studied for it, then that means that 28% did not study for it. For those who failed, we said that 31% studied for it, which means that 69% did not. All right, makes sense? Now, to find the probability of both of these things occurring, failing and studied. So what percent of the class failed and studied? Well, we just multiply, and I recommend doing this for all of them. Okay. So we find that about 6.2% of the class failed it and studied for it. And studied for more than 3 hours, I should say. How about those, what percent of the class failed it and did not study? Well, about 13.8 of the class. And when we add these two up, notice that they add up to our 20%. What percent of the class passed and studied for it? Hey, 57.6% of the class both passed and studied for more than 3 hours, what they should do. And then those annoying people who passed but didn't study as long for it, well, that would be 22.4% of the class. Those people are so annoying, right? Right. Now, how do I find the probability that a student studied for it for more than 3 hours? Well, I take all of the scenarios where I see studying, and I add those together. So 0.062 plus 0.576, when we add those together, That's the probability that we study, and that's going to be equal to 0.638. How about the probability that a student doesn't study? Well, we could do 1 minus this, right? Or we could add up the scenarios where not studying is happening. When we add those up, we get 36.2% of the class does that. Right? Now it's asking, okay, given that a student, or if a student studies, what's the probability that he passes? Well, what is that? Well, that's the probability that given a student studies, they pass the exam. So we're going to find the probability that we pass and study over the probability that a student studies, which is pass and study is 57.6% chance of that happening over the probability that they study. Hey, I calculated that up here. 0.638, and we find that if you studied, the probability that you pass for more than 3 hours, the probability that you pass the exam was 90.3. Okay. Next one, find the probability that if a student doesn't study, what's the probability that you pass? So we're looking for the probability that you pass given that you didn't study. Well, again, it's going to be the probability of pass and not studying over the probability that you didn't study. So those who passed and studied, or and did not study rather, was 22.4%. Probability that you didn't study was 36.2%. And when we calculate that out, we actually find that for those who didn't study, 61.9% passed. Interesting. Because the teacher's just really, really good. Right? I'm going to let you work on this, on the last one on your own. You can check the key for the answer. Right? Hope you have a wonderful day, and thanks for listening.